All right, our chair, Professor Siddiqui, is traveling today, so I have the pleasure of introducing today's speaker. My name is Yuri Kolomensky. I'm a particle and nuclear experimentalist. And I've known Professor Lindley Winslow, not in that exact capacity, for over 20 years. Lindley is currently a professor at MIT, but she started her academic journey like many of you younger people as an undergraduate here, graduating with BA in physics in 2001, and then deciding that California is too good to live for and staying here for a PhD. She received her PhD with Stuart Friedman in 2008, working on the Camland detector in Japan and measuring the properties of elusive neutrinos and the oscillations over space. So over her career, Lindley followed, I think, Stuart's footsteps relatively closely, but in reverse, right? From neutrinos to axions and to other new physics effects. She was a faculty at UCLA until MIT made her an offer she couldn't refuse. And she's currently a professor at MIT and specializing in using very large detectors, neutrino detectors, to study fundamental properties of matter, to very small detectors that she'll talk about to study fundamental properties of dark energy. And so with that, let me introduce you Professor Winslow.
Wonderful introduction. The sound sounding okay? Okay. Yeah, so it's a real pleasure to be here. It feels like some sort of victory is having sat there for many, many talks to be down here. And always my favorite thing is to wake up and see the campanile. And so it's been a good day, and I hope you guys enjoy hearing about wavy dark matter. All the opinions are my own, and I'm speaking for myself as I see some of my wonderful collaborators in the audience. And I look forward to discussing afterwards with them, as Ben is smiling at me already. Okay. Excellent. So as Yuri said, my physics is sort of divided into two different areas, axion dark matter searches and neutrinoless double beta decay. I would really love to find new physics at the gut scale, and that is one of the main motivations for these two topics. I also am an experimentalist, and so I really like to build things. And so the things that my lab works on are photodetectors, hot and cold, well, warm and cold, quantum dots, crystals, magnets, and dilution refrigerators. And I feel like at some level when you put crystals and magnets in a talk, it's like, did she grow up from being 5? And apparently not. We still play with magnets and crystals and things that glow under dark lights. And so I think the question really is, as an experimentalist, how do you put these together and try to force the universe to answer some big questions? And so what are these big questions that motivate both these two topics and my work as a whole? And that is, what is dark matter and why is there more matter than antimatter? And I can't resist not showing pretty pictures. I love pictures of experiments, but not everyone does. But I love this picture, particularly this is the new sort of deep field from Hubble, because while staring at it, you see those two questions I just put for you. So the first one, what is dark matter? What sculpted all those galaxies? What is causing the lensing of those galaxies that you see in that picture? And then if you start and stop and really think of this as a particle or a nuclear physicist, you start asking the question that's all matter out there. What happened to all the antimatter? And then you're even more perturbed. And so we'll go from there.
Excuse me.
Yeah.
Could you use the microphone, please?
Yes.
Yeah.
Okay. So we're going to swap out. Okay. Here we go. So does that work better? That's much better. Okay. Excellent. So we're still staring at the beautiful picture and admiring those galaxies and thinking deep thoughts about the universe. And so how, as an experimentalist building experiments here on Earth, at least for the time being, can we go after these big questions? And so that brings us back to the two things I'm interested in, axion dark matter and neutrinoless double beta decay. And so for today, my main focus is going to be on the axion side of the program because I see a lot of my collaborators that can tell you anything you want to talk to you about double beta decay. So where are we in the search for dark matter? And so for many of you who are aware that high energy physics just went through their big decadal review, and dark matter featured very prominently in this review. but it can still feel like a zoo. There are a lot of different candidates, a lot of different experimental techniques, and so I might have young children and I end up reading Curious George Goes to the Zoo more often than I would like. And so I looked at this picture and I'm like, that does sort of illustrate some of the, I think, issues that many people have with dark matter. What I would offer and argue is that zoos are actually very organized places. If you want to find the elephant, you go to the elephant exhibit. If you want to find giraffes, you go to the giraffe exhibit. And so what we have been doing in dark matter for many, many years is looking for elephants, and elephants are wonderful zoo creatures. But there are other things at the zoo, and how do we find them? And so there are some candidates, like you could compare to a platypus, and if you were in Australia, that's where you should look for it. But within this sort of zoo of dark matter, there are places that are more likely to look. And so we have elephants, and I would argue that axions maybe are giraffes, like very good animals. They have some interesting features like long necks, but are very interesting to look at. I also particularly like this drawing because all of the animals are holding balloons, and part of this sort of metaphor, and you can tell me afterwards if you like it, is that one of the things you might be feeling as you hear about dark matter experiments is that each experiment seems to have their own balloon, and that often is some sort of quantum sensing technique, especially if you're looking for new candidates for dark matter. And so you're not wrong. All of the animals are at the zoo. There are still some animals that are better to look for, and yes, they all have balloons, but that's what actually makes it fun and exciting. And I would argue that it's still really great to look for elephants, and we also can look for other things. So the goal of the talks today is to describe a suite of experiments that are required for a definitive search of the axion. There will be a time when we need to stop searching for axions and go looking for, once again, other creatures at the zoo. Understand how they relate to different regimes of quantum sensing, why do you need all these different techniques, and connect an axion discovery back to key questions in particle and nuclear physics. And so, and then tell you about my particular program, which is ABRACADABRA 10 centimeter, what we ran at MIT, and then the greater DMRadio program. So, yes. So I hope you guys enjoy. So wave-like dark matter. Wave-like dark matter is any dark matter candidate with a mass less than 1 eV. And so they fall into broad candidate categories based on their charge parity symmetry. You can just know that they come in these categories of pseudoscalar, scalar, and vector. When you are in this very, very light regime with these really light dark matter candidates, you might ask, how can they actually do their job of being dark matter? Didn't they fall out of thermal equilibrium in the early universe? The answer is that it's a different production mechanism. These candidates were never in thermal equilibrium. It's an athermal production. And so if you're looking for this type of candidate, you're going to be looking at a very different detector design. And so you're going to look for some sort of coherent interaction of the wave with your detector and looking for some sort of resonance to increase your sensitivity. And so the most famous candidate among your wave-like dark matter candidates is the QCD axion. Let me tell you a little bit about the QCD axion. So if you can excuse for a second a quick deep dive into some particle physics, it was originally introduced, this additional U1 symmetry, like sort of the electromagnetic force, to preserve CP in the strong interaction. We actually have a problem that the strong interaction always conserves this quantity. And so it was natural that if you introduce this new symmetry, that it would produce these particles, and it was realized that these particles, the QCD axion, could be a good dark matter candidate. So it's very nice. It's solving a problem over in the QCD and the strong interaction, and now you have a bunch of particles that could be dark matter. And so this particle would couple to photons, nucleons, and electrons, and it can do its job with a broad category of models. And these two models are referred to by their letters, KSVZ and DFSZ. And I'm sorry, that's really hard to pronounce, and I hope I get the letters in the right order through the whole talk. But yes, DFSZ is the one we normally talk about. And what's neat, these introduce heavy quarks for the KSVZ and additional Higgs fields for the DFSZ models. And so the classic plot that you're going to see in every single axion talk is a plot of the mass of the axion, because this theory doesn't tell you what mass it is, versus the coupling to something, and it's often the coupling to photons. And we can talk a little bit more about that. And it always will show up as this yellow band you see here in the parameter space. And so all your experiments are going to be pushing down in sensitivity until they reach this band. And once you cover that band, you are done. there's not much reason to search below that yellow band. And so that's one of the things that's very attractive to axion physics, is that you have an end spot. You don't search any more below that. You also have bounds roughly coming to first order from astrophysics at the lower edge around 10 to the minus 12 and at the upper edge around 1 eV. Excellent. So this is where we're starting, and let's talk a little bit more about it. We also have a broad category of particles of candidates called the axion-like particles. They are similar to the QCD axion, and they're produced in many higher order theories. My understanding, others here have better, is that it's actually hard not to make them. And depending on the details of the theory and the cosmology, they would be in this blue band and push up. And so what's nice is on your way down to the yellow band, there's lots of places that you might make a discovery that might in some respects be even more interesting than the QCD axion. So in summary, there's a lot of interesting things to look for, from the QCD axion to these Alps. Sometimes we just refer to them as axion. And we have a very clear parameter space to look for them in, 10 to the minus 12 to 1 eV. Those are your masses. And what's 12 orders of magnitude among friends? Okay. I'm going to try to convince you that we need like 5 experiments. And you can tell me at the end if you believe me. So how do you actually build an axion detector? This is where it really gets fun, I promise you. So as particle physicists, we often think of things as particles, go figure. And what we often look for is this heavy dark matter. You might think of the sort of billiard ball model. When you start talking about these particles that are wave-like, axion dark matter with masses at 1 eV, you might try to still think of things as particles, but really what you need to start thinking about are waves, and how do you build a detector for waves, for fields. And so this is adapted from a slide from Ben Softy, so thank you, Ben. If you start writing down the actual de Broglie wavelength for these particles and the occupancy number, if you take a sort of nano EV axion, you end up with a sort of 10,000 kilometer wavelength, and occupancy numbers of 10 to the 44. Versus if you take a sort of classic WIMP-like model with a mass of 100 GeV, you have wavelengths of 10 to the minus 16 kilometers and occupancy numbers at 10 to the minus 36. So if you can compare these two mass ranges, it becomes very obvious why we call this wave-like dark matter. These things are waves. They are very much waves. They are no longer particles. And you're going to be building a very different style detector. Yeah. So let's start actually measuring waves. So if you're measuring a wave, you're going to have to start getting comfortable with frequency space. You're no longer going to have a detector that clicks or counts stuff. You're going to have a detector that has some frequency spectrum. So when the axion is created, it's created with a wave with a frequency proportional to its mass. So if you build a detector, what you're looking for is, of course, you always have some sort of noise floor in your detector, because that's the nature of making any experimental measurement. And at the mass of the axion, and I told you had this whole mass range from 10 to the minus 12 up to 1, you're trying to look for one peak with a width that is incredibly narrow. It's basically 1 part in a million. What's very nice about this signal, above whatever background is in your experiment, is it's very hard for natural sources besides the axion to mimic something so narrow above your background. What's even neater about this signal is that it has a very distinctive shape due to the velocity of the axions in the halo. So it's not even that you're just looking for a spike, you're looking for something with a very distinctive shape. So as an experimentalist, you get very excited because this makes your analysis easier. And so this is where we're starting. So if you ask why are experimentalists excited about this, this is why. You have a very clear signature. You don't know exactly the frequency range. That's still a problem. We still have those 12 orders of magnitude. But we know exactly what we're looking for, and it has a very distinctive shape relative to the other things. So you might ask, is there any theoretical preferences here? There's 2 cosmologies that you can work in. You can have your axion made before inflation or your axion made after inflation. As an experimentalist, I kind of wave my hand about this. With inflation, you have a lot more freedom because it sort of effectively mixes up your early universe. There's much more technical ways to describe it. And post-inflation, you're just more constrained. And so this gives you some guidance, but not a whole lot of guidance. Then you get extra guidance from things like astrophysics. And so black hole superradiance, we can talk about that afterwards if you'd like. And then the classic sort of bounds that come from overcooling of stars if you pull out too much energy in axions. So this gives us basically two areas we can look. We can look post-inflation, and we can look here. This parameter space is A, very hard to reach experimentally, and B, is at some level less motivated, and so hence we tend to focus at sort of 10 to the minus 12 up to 1 eV. So now we're back to this is where we look. We have some guidance between 10 to the minus 12 and 1 eV, and two cosmologies, one before inflation and one after inflation. So what makes it difficult is that once again, we have this wide band. And so we're often used to, in particle physics, of building one massive detector that can do a bunch of things. And so you can think of ATLAS, you can think of CMS, even like Cori and Cupid, they can do more than one thing. But here, we're looking for a wave. And if you think about making analogies to the electromagnetic spectrum, would you expect a detector that was built for radio waves to work the same as one for optical, to work for gamma rays? And if you asked one detector to do that, people would tell you you're being silly. And so now if you ask a wave-like dark matter detector to do that full parameter space from 10 to the minus 12, that is equally silly. You know, as you move through different frequencies, your readout electronics, your receiver, all of this has to be updated. So once again, that feeling of being at a zoo might be a little bit true in that you have multiple experiments to go after the same thing, but it's completely a responsibility of the fact that you're looking for waves. That you're going to have to tune your detector to the waves that you're interested in. And if you design it well, you could get a couple of orders in frequency space, but you're not going to be able to do the full with just one detector. And so I hope that's a nice analogy. And also I get to show a rainbow. So then the question is then, how does the axion actually couple to matter? And so you get a couple options. If you write down all of the axion's couplings, and I'm sorry about the Lagrangian, but it's always the easiest way to do it. You have a coupling to photons, a coupling to the nucleon EDM, a coupling to the axial nuclear moment, and a coupling to the electron moment. All of these three are possible, and there are ideas, but if you're an experimentalist and you can couple to photons, measuring photons is very easy. We are very good at measuring photons. Now we're back to that spectrum, and you can build a detector. And so if you ask why axions are going after the photon coupling, it's because it's easier to measure photons. These other couplings do exist, and at some level, they are actually more critical for the QCD axion and the interaction with the strong force, but experimentally, this is where you would start naturally. So that's what we're going to focus on for the rest of the talk, is this coupling to photons. So yes, a principle that others, I think, would agree with, but there's some very interesting work being done on the others, on the other couplings. So if you're looking at the coupling to photons, that is electricity and magnetism, and I feel like in this room, it's like the echoes of Maxwell's equations are just coming onto the slide all by itself. We can write down axion, and then you can write down the modified axion equations. The terms you gain, several of them are proportional to the gradient in the axion field. That will be small, and then you're just left with the modified Ampere's law. And so now you are doing electricity magnetism calculations. And so, as with most things in physics, you can do easy calculations or hard calculations. And depending on the wavelength of the axion you're looking at, you are looking at intro E&M. I don't know if it's still 7B, but yes, something like that. You're looking at 110A, or you're looking at the graduate course Jackson E&M. And so if you're in a regime where your detector wavelength is much, much bigger than your experiment, you're in the so-called quasi-static regime with effective currents. And so this is intro E&M. You can do right-hand rule with it. And in fact, we will do that later in the talk. If you're in this regime where the wavelength of your axion is about the same as your detector, you're in the cavity regime, and this is calculations on cavities. And if you're in the regime where your wavelength is much, much smaller than the size of your detector, you're in the radiation regime. And these are very hard calculations, and there's some in the field that would think that maybe we still haven't done those quite correctly. And so it just gets harder as you go up here. Thankfully, I have a penchant for this longest wavelength, which is a little bit easier, though it borders on the cavity regime sometimes, and that makes it more exciting. So the quasi-static regime, these effective currents, and you're going to be seeing detectors like this one, The cavity regime, where literally you're looking for the axion to photon coupling exciting the cavity, and you're looking at experiments that look like this one. This is ADMX. And then finally, these sort of so-called dielectric haloscopes where you actually force the conversion and are receiving photons. So where are we as a field? So the current bounds, this is a lot of stuff on one plot. I feel like, but it's very pretty. So once again, this is the plot. It's mass of the axion on this axis and the coupling of photons on this axis. The yellow band, that's our goal. That's what we want to cover. We have a couple experiments. These are the so-called cavity experiments, ADMX being the most long running, that are beginning to poke in and rule out some of this DFSC space. And then we have big bands on either side that need to be addressed. That is very complicated. This is a slide that came after the snow mass, and it's very easy now to read off. So more than a decade ago, we had no experiments that were reaching the DFSC or the QCD axion band, the KSVZ axions. We did have some bounds from astrophysics. And so now we currently have a handful of experiments that are reaching the DFSZ, and now the question is, how do we grow bigger? There was a call several years ago by the Department of Energy for these new dark matter new initiatives. They sort of funded a handful of experiments that ranged from sort of light MeV dark matter to the axions to some fixed target experiments. And so of this effort, 2 axion experiments were funded, and so they're DMRadio cubic meter and this ADMX EMFAR. So in the next 2 years, we're hoping that these experiments will get started and start moving. And I'll tell you more about DMRadio a little bit later. And so next, we're talking about experiments to fill this whole band. And so here, what you're going to need is a lot of cryogenic infrastructure, high field magnets, and high Q cavities, and beyond the standard quantum limit readout, BSQL readout, and some very fancy readout. And so once again, why does it feel like a zoo with balloons? And a lot of it is coming from the fact that you're going to need this very fancy readout to build these experiments. And so when I talk about BSQL readout, what does that mean? Beyond the standard quantum limit, as you all well know in this audience, quantum mechanics sets fundamental limits on how well we can measure 2 variables. But you can play tricks and squeeze or push the noise into variables you don't care about and do a better job measuring about the variables you do care about. And so depending on the frequency regime, and so I took this from one of my collaborators, you're going to use different types of this BSQL readout. So once again, the expectation that you could use one type of quantum sensing, quantum readout for the entire frequency regime is a little bit naive. You're going to need different techniques. And so this is the issue, is that depending on the frequency range, you're going to need different BSQL readout and different detectors. And so that is why you have these sets of experiments in order to do that definitive axion experiments. And so that's why you will see a huge list, and you might hear about more experiments every single day, because each of those experiments is trying a slightly different geometry with a slightly different BSQL readout to try to get after the parameter space that's not going to be covered by these 2 experiments or the current experiments. And so that is your quick overview of all of the different things you might hear about from now until till next week. My guess is you hear about at least one more by next week. So in summary, my review of an incredibly vibrant new, vibrant growing field is that for axions, you have two cosmologies, this pre-inflation and post-inflation frequency. You have about 3 frequency regimes, this is my summary, and 3 noise regimes. And so this combination of 3 frequency regimes, 3 noise regimes, I predict that we need about 5 experiments to definitively cover this regime. And now I'm going to want to tell you about my experiments within this. So before I tell you about my experiments, trying to sort of communicate why it is that we are particularly excited about the possibility of a discovery for axions. Oftentimes when we're in the dark matter field, we get obsessed with setting limits and how big of a detector we can get and set a limit. And we often forget, I think, to remind ourselves like what it is that we actually would discover and what then would be the next steps after we make that discovery. So this is my attempt to do that for you and convince you that this would be incredibly groundbreaking, not just for dark matter, but for the field as a whole. So if a QCD axion was discovered here at this frequency, range, and these would be cavity-like experiments. This was a QCD axion that was made after inflation, and it would predict expanded Higgs sector or more quarks. And so right away, you would know that we need more particles in the standard model. The next step would then be that you would like to determine that this really is the QCD axion and not an axion-like particle, one of these particles made from other theories. And so you would want to test the nucleon and the electron couplings of the axion. And then the last part of this is I told you that the shape of that signal is very distinctive. Immediately, you would actually be able to do astronomy with it and start mapping out the dark matter halo by the shape of that signal. And so it would be really exciting once we make a measurement to be able to do that. If you see an axion down here, this is an axion that was made before inflation. It's clear proof of new physics at this energy scale, this very high energy scale. And it would predict, once again, this expanded Higgs or expanded additional quarks. Immediately, you would know we had more particles to look for. In this regime, you would actually start affecting cosmology and what you might see in an experiment like CMBS4, which is interesting. And then, once again, you need to test the nucleon and the electron couplings to make sure you really have a QCD axion. And then you could still do that thing where you look at the halo shape and you start doing dark matter astronomy and looking for things like dark matter streams, et cetera. So then the last one, and the one that I would be really excited to find, not that I wouldn't really want to build that, the ultimate experiment that discovers that the axion I saw there, would be discovering something that shows up in this parameter space. And so this is an axion-like particle. It's not the QCD axion. It's proof of some higher order theory. And the possible signatures would exist in accelerator-based experiments too. And so once again, you would need to build more experiments to test the other couplings. And you would have to look at the line shape and see if it matches what you expect from dark matter. So all of this would be really exciting. But all we have to do is discover the axion. And so this is why, in the last few years, you've seen and heard a lot more about axions. And this is a plot that I love, made by John Ouellette, of the number of abstracts to April meeting for axions relative to WIMPs. And we're catching up. I think we caught up in the last few years. And if you're curious about everything I laid out here, there were several community white papers that were put out there and can summarize in all the details all of these things. So at that point, I hope I've convinced you that wave-like dark matter is really interesting, that there would be huge consequences for discovery, and that it's obvious that we should build a bunch, namely at least 5 axion experiments to try to find this thing. So now I can move in and talk about my own experiments. So the experiment that ran at MIT is ABRACADABRA, and it actually does stand for something. And thankfully, I have my slide in front of me, so I don't miss one of the A's. I always drop one of the A's. So it's a broadband/resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. So it's actually also telling you exactly what we did. And I thank Jesse Thaler, who really loves Scrabble, who came up with the acronym. And so this is what we built. And so what are we going to go after, and what is this B-field ring apparatus that I'm talking to you about? So this is, once again, the parameter space for axions. And ABRACADABRA is going after these nano EV sorts of axions. And so something like 10 to the minus 12, 10 to the minus 14 to 10 to the minus 6 is the parameter space that we were going after. And so if we remember about our 3 different kinds of wavelength regimes, this is the regime where the wavelength, the mass is much lighter, longer wavelength is much, much larger than your detector. And so things to keep in your mind as we talk. And once again, also in your cosmology, this is the pre-inflation axion that you're going to look for down there. So we're going to choose this so-called quasi-static regime and this detector that you see here. So abracadabra, what is that B-field ring apparatus? So here's your B-field ring apparatus. It is this toroidal magnet, and if you remember your Ampere's law, the B field, the axion will couple to the B field, producing an effective current that runs around your toroidal magnet. And I promised everyone that we would, in fact, do the right-hand rule, which is important not to do with your pointer in your right hand. You put your thumb in the direction of the B field, curl your fingers, yes, this is like the echoes of all the intro E&M. What's going to happen if an exact axion exists and like not enough people are doing their right-hand rule right now, is that you're going to create a real magnetic field up through the center of your toroid, where classically there should be no field. And as an experimentalist, doing a measurement where you know you should have zero background is always the goal. It is always the perfect measurement. Does nature always provide us zero background? Not really. Will there actually be zero background? Unlikely, because any experiment worth doing is probably hard. And so the real question is, what would be the backgrounds? What would simulate an axion signal where classically there should be no axion, there should be no signal? And that is the big question as an experimentalist you need to address. And so once again, reminding everyone that we're looking for wave-like dark matter, and we're going to look for a spike with a very narrow width, with a very determined shape, that's about 1 part in a million above whatever backgrounds we do have in this detector. So what do we need to get started? We need a magnet. We need something to get the magnet cold and something to get our electronics cold. We're doing precision measurements of electricity and magnetism. So the thing you're going to grab is a squid current sensor. That's obvious. And then finally, some vibration isolation and some warm and cold shielding to get you out of place. And so this is the list. It's a very easy list to write down. And if you call up NSF, they have this nice type of award called an eager, which they can give to you if it's under $100,000 without a big review. Just FYI, a good thing to know about. And so that's what we did. I had a dilution refrigerator, thank you. Got the magnet from NSF, bought the Magnecon current sensor. You can buy squids off the shelf sometimes. And then we put in place a little bit of vibration isolation and some warm and cold shielding. And so the question is, was it as easy as I made it out to be? Of course not. But we were able to start it and put it together. And so this is how we built the magnet. It's actually made out of little pieces of Delrin that are glued together to make a support structure that you can wrap in. You connect a loop around a Teflon tube down through the center, and that is your magnet. And so here's a picture of it assembled with a lot of epoxy to hold all the wires in place. A 1 Tesla magnet is about 1 kilometer of wire, so you have to do something to keep it in place. So it was installed in the fall of 2017, and it didn't work. And so we did some improvements to the geometry to try to actually keep the loop through the center that was picking up this induced axion signal a little farther away from the magnet, and put it in place. While it was there, we increased the vibration isolation. And so the whole experiment, instead of being mounted to the coldest part of this dilution refrigerator, is hanging from a Kevlar thread. So quite literally, my entire experiment is hanging from something that looks like a piece of dental floss. And so just to get you away from the natural vibrations, either in the room of people walking around or the dilution refrigerator's mechanical cooling. And so this is what it looks like installed. And so the magnet is sitting in this spin-coated copper shielding. And if you look very carefully, you can see a little wire running up. The squids sat for this run at 700 millikelvin for aficionados, and you can see sort of a loose coupling thermalization of the whole structure to the mixing chamber. One note, this is a very large thing to cool with a dilution refrigerator. I don't recommend it. So Oxford, who made the fridge, periodically brings people by to show them that this fridge is capable of doing that, and it's like a little museum tour. So that's for those in the room that really use a lot of dilution refrigerators. They can appreciate that. So the last problem, or last question for building Abracadabra was you have this signal coming out of this pickup loop to get that flux that's coming from your possible axion. How do you get it to your current sensor? And there's 2 possible readouts. You could do a broadband readout where you directly take the loop and couple it to your squid, and so at that, you would measure all frequencies at the same time. And that's easy. The other option is to do a resonant readout where you couple your pickup loop, your signal loop, through an RLC circuit into your squid. The nice thing is that you enhance your sensitivity by the Q value of that resonant circuit. And so that's very nice because you could, in principle, have a very high Q resonant circuit to do that. The problem is that that takes engineering and to build stuff. And I don't know if you guys picked it up that the whole budget of this experiment was about $85,000, of which $80,000 went for a magnet and $5,000 went to a current sensor. So part of this was necessity, and part of it was we didn't know what the backgrounds would be. So in some respects, for a Pathfinder experiment, doing the broadband readout, where you see all frequencies at the same time, is actually the place you want to start. Because the question really was, what will you see in this experiment? And so it's two-pronged. I can tell you that we really wanted to build an experiment that saw all these backgrounds, or I could tell you that we just didn't have enough money nor time and resources to build the resonant readout. And so that will go to things I'll tell you about next. So, excellent. So we went with the broadband readout with off-the-shelf squids. I love saying off-the-shelf squids. And for those that are in the room that really love squids, there's some more details. And so then the last part of this is you have to do some electromagnetic shielding, otherwise you'll just see all the noise in the room. And so we lined the dilution refrigerator with mu metal shielding. Once again, there wasn't a huge budget for this project, and so MIT used to run a small linear collider, a very small one. And the postdoc and the graduate student went up and harvested mu metal off the old collider and brought it down to our lab and wrapped the dilution refrigerator. So fun story of how to get it, but this sort of tells you this was very much a Pathfinder experiment to see if the concept could work, and therefore was it worthwhile continuing to do the work. So with about 2 years from the first time Ben walked into my office to the first results, that's what we did. And so this is the data from the first run of ABRACADABRA, and I show this to you because it's actually the cleaner data, though not quite as sensitive as our second run. And it's just so beautiful as an experimentalist. So what you have here is the frequency that was read out in that broadband readout, so you're seeing all the frequencies at the same time. At low frequencies, you're seeing this sort of forest of lines, no axions discovered. And to first order, that is just sort of the shaking of the magnet in the fridge, and other sorts of low frequency noise that you get. At high frequency, our sort of running theory is that some sort of electromagnetic noise, and beautifully though, that there is this nice region where we are at the theoretical noise of the squid that we bought from MagnaCon. And so that is sort of proof that this concept works, that you can put together all of these little pieces and not take much care, and you actually do reach the fundamental limits of your readout electronics, of your readout squid and the data acquisition system. And so that was very exciting, and you can turn then this data in frequency space and go ahead and convolve it with an expected signal, and so that's the signal that you might be able to pop out over the noise. Notice the incredible zoom in frequency space, and pull out a signal. Of course, this is an experiment, so we have to calibrate it. And calibration is one of those things that's incredibly difficult and not that interesting. So I won't bore you that much with it, except that we quite literally have a ring and we inject axion-like signals into the detector, and we do it at a whole bunch of frequencies and a whole bunch of heights, and model this with something like COMSOL and figure out what the gain and the detector response of this thing is. So we did calibrate it, but not the hardest, but not the most exciting part of the talk. And so then going to the more exciting part, a really detailed statistical analysis done with the help of Ben Softy, who is sitting here, and a student, Josh, to actually pull out rigorously the axion signal. So doing a full mapping of searching with the axion template for the axion signal. And so with that, actually turning this into a limit on GA gamma gamma. So you probably would have heard more if we had actually found an axion. So we saw no 5 sigma excesses that were not vetoed by magnet off data. And so the beautiful thing of axion searches is you can turn the magnet off and get your background. So once again, a nice thing about doing these. And so 87 mass points out of over 1 million taken out with the magnet off data. And so here is the limits for run 1. And for something that's the size of a grapefruit, it was doing an incredible job coming close to the sort of best bounds in the field at the time. And so to give you an idea of what ABRACADABRA was able to do, so once again, this is the mass of the axion versus the coupling to the photon. This is the limits from run 1 of ABRA. This bound here is from a so-called solar or helioscope experiment, axion experiment. It's an LHC magnet on a little cart that points at the sun constantly. It's very large. These are the sort of state-of-the-art cavity-like experiments. That's ADMX. And so once again, here's like the little experiment that did an incredible job with just putting it together with a magnet and an off-the-shelf squid and some shielding that we took from an old accelerator. So we did do a second run 3 of ABRACADABRA. This was led by my graduate student, now Kai Pak Fellow at Stanford, Chiara Salemi, and the junior graduate student at the time, Callie Ray Pappas. And so the difficulty is we wanted to increase the overall sensitivity of the experiment, so we went from a loop to a cylinder. This took an incredible amount of work, an incredible amount of simulation with COMSOL, and a lot of details of actually how do you connect wires onto a superconducting cylinder, which was fun. But the issue is, of course, if you increase your sensitivity, sometimes you increase your sensitivity to noise. And so this ended up being a much more difficult run because of that. But we were still able to extract improved limits with improved sensitivity. So we improved the overall sensitivity by a factor of 4 to 10, as we expected from simulations. And in some of the parameter space, especially that really interesting nano EV parameter space that I love because it corresponds to a gut scale axion, and I really love gut scale physics, we were able to sort of set some of the strongest limits in the world. And since we haven't run anymore and no one else has, they continue to be the strongest limits in this particular part of the axion parameter space. And so this is the ABRACADABRA team, and you might recognize some of the people here. And so then you might ask, what's next? And so this is where I move over to the DMRadio collaboration, which is a Berkeley, Stanford, MIT, Princeton, and you can see the rest of the introduction here. And this is the question of how do we improve upon this detector? How do we build something bigger? So going through my list of what you saw earlier in the talk, what we need now is we need a bigger magnet. We still need a dilution refrigerator. We're going to need to move to that resonant readout. Really the way you gain is to move to resonant readout. Of course, this is hard, and this is the part that hasn't been done before. But we're going to continue to need some vibration, some warm and cold shielding. And this is the DMRadio program, which is how do we do a definitive search for axions in this parameter space below 1 micro EV. And these are the experiments that I'd like to tell you now, and what they're doing and where we are with them. So DMRadio 50-liter construction is underway. There's a typo there. It's 2024. I forgot the year. And it will do science runs in this ALP-like parameter space and be a test stand for quantum technologies, namely to test this resonant readout. If you're looking for the next larger experiment, this is this DMRadio cubic meter experiment. This was the Dark Matter New Initiative experiment I told you about earlier. And so it'll be the first of these experiments to actually go down to DFSZ in this parameter space, so this sub-micro EV parameter space. But the issue is for a magnet of this scale, so a magnet on an order of meter cubed that can fit within the budget of the Dark Matter New Initiatives, you were forced to move to higher frequencies. And that, as I said, as you move in frequency, you have different complexities. And so you're moving from sort of kilohertz up to megahertz, and that's added complexity. And so we've been doing detailed modeling of the response of this detector and working to understand how to build it. So at these frequencies, you actually need to move to a different geometry. You hit fundamental limits of what you can reach in the toroid. And so we're moving to this solenoid-type magnet instead of a toroid. And so this gets a little more complicated, but it still follows the right-hand rule to first order. So solenoid magnet with a B field pointing up like this. You're going to get an effective current running up and down like this. And so you're going to get an effective magnetic field that's running cylindrical in the direction that you see there. And so what you're going to need is this more complicated cavity-like structure, this what we call a coax, to read out this effective B field. And so it's going to end up with currents running around as you see here. And so at this point, what we're working on is a detailed engineering drawing and the accompanying sort of documents that you need for DOE, including a TDR to actually go after this experiment that's on the order of $25 million to build. Then that leaves the sort of ultimate experiment that you would want to do in this parameter space. And so this is what we call DMRadio gut. And so it's the one that would take you down to DFSZ all the way down here at a nano EV. And so the issue here is to get to such small couplings is that you're going to need a really large magnet. And so our current estimates are a magnet on the order of 10 cubic meters with a 16 Tesla field. And so if you would like to talk to me more about that, that will be the subject of tomorrow's RPM up at Berkeley Lab. And at the same time, if you're going to build a magnet of that size, you're still going to want to do very detailed quantum readout of this thing, and how do you actually do that at these frequencies? And so also a nice subject for another day. And so what you see here is a progression of experiments to something that's being built right now, and to something that we're hoping to build in the next 2 years, to something that is sort of a 10-year R&D plan with a proposal hoping to happen in sort of the 2033 timeline. It might be in line, for those that know, with the next P5. So at that is the DMRadio program. That will be the definitive measurement of the axion below 1 micro EV. And I'd like to open up for comments and questions.
So, any questions for Lindley?
What kind of capacitor are you planning on using? Is it going to be a variable capacitor?
That's a very good question, yes. And so that is exactly one of the issues, is how do you control a capacitor? And so if you work backwards to the capacitance and inductance, these are not surface-mounted capacitances and inductors. The capacitor that you need is about this big, and the inductor is about that big. And so you're cooling all of these things down to millikelvin temperatures. And so this is the big research effort at our colleagues at Princeton, who have been studying sort of the ultimate limits of Q for these sorts of resonators. Yeah. That's the active area. You can use a yeah, like yes. So you have a couple options. You can actually move plates. You can actually do like a butterfly capacitor. We've tried all the ideas, and I think we're trying to figure out actually what the easiest one to manipulate at 10 millikelvin is. Yeah. So if you ask what 50-liter needs to prove and why Abracadabra didn't do it, it is how do you manipulate a capacitor and an inductor at millikelvin temperatures reliably? Megahertz, kilohertz to megahertz. Yeah. Yeah.
Yeah, if you see something, then how does that guide the searches in the electron sector and the nuclear sector?
And I'm like, I see Dima smiling behind you. So my dream of that nano EV axion is because that would be sort of a perfect, it would be hard for Casper, a sort of an NMR style technique to go after it, but it would very much motivate figuring out how to build the NMR experiment at that level. Up at the highest frequencies, if you're talking about that post-inflation axion and gigahertz frequencies, that is much more speculative, but I completely believe in our ingenuity if we saw an axion to figure it out. And so I would also point out that there is a part of the parameter space down there at 10 to the minus 12 that can probably only be reached by the NMR style experiments. And so there's sort of DMRadio gut and then a little bit of Casper, and that would be one of those 5 experiments that I said. But as soon as we see a discovery, the NMR style techniques become critical because you want to know if it's the QCD axion or not, or whether you have, some other higher order theory at work. Yeah. Yeah.
What kind of power do you expect on your periodogram? Will you have any resonant peaks or anything?
That is an incredibly good question because the answer is when we move from sort of abracadabra frequencies at sort of a kilohertz to megahertz, you do start seeing these cavity modes that show up. And so as I look to the back as Nicholas is sitting there among my other DMRadio collaborators, we have spent a huge amount of effort really understanding what how you tune and use different coaxes to avoid that sort of resonance structure that would get in the way of you being able to see an axion at those frequencies. Yeah. It's a huge amount of electromagnetic modeling to get these experiments right. And that was a lot of the calibration stuff that I left out. Excellent.
Go off the wall, but is it helpful to like run multiple of these cavities at the same time?
Yes. And that's actually, if you ask me, one of the questions we actually need to answer with DMRadio, gut, is whether we need one magnet or whether you would build this, because it's magnetic field and volume. Could you do it with like multiple large magnets? And then if you start moving the magnets, there is a coherence length, there's natural axion lengths, and you could start doing effectively interferometry with them. Did I get that right, Ben, as you nod up there? Yes. And so that in itself, like if you made a discovery, you would want to start testing those properties of the axion too. You should be able to say that it would be coherent from here down to Caltech, but not to MIT. Yeah. Yeah, and you get some, you definitely can do, like you get a little bit of an enhancement just due to the statistics of combining two experiments, yeah. And so that's just always the question is, do you build lots of little ones or do you build one big one? And I think at times I get biased because but there's no self-shielding equivalent for axions, I think, but that's what we need to work out. And that's why gut is like a 10-year project, is that question is not at all answered. Yeah. Other questions?
I have a question. So in the toroidal coil picture,
Yeah.
we send a B field through the toroid, right?
Mm-hmm.
We use a current that's in the same direction as like it flows in the toroid itself. This is different from the regular picture of electrons where our B field induces a force that acts orthogonally to electron motion. So does that, how exactly do our B fields couple with our axions such that this is different?
I got a little bit lost, but it's quite literally, it's an effective current. So it's like a current was running in a loop around your toroid. And so it is as simple as a wire carrying a current, you can think of it. And you can just literally do the right-hand rule. So it works, but it's odd that you end up with this effective current that can create a real magnetic field. And that is the sticking point that feels a little bit weird, but it is the way the theory works. Every once in a while, nature does things that are just not intuitive, but the math works, and that's how it works. Yes, effective currents. That's the first thing you have to accept when doing an axion experiment. Yes. Excellent. Okay,
So maybe
thank you.
let's thank Lindley again.